Hello students. In previous lecture we have studied concept of equivalent sets. Two sets A and B are said to be equivalent if there exists a bijective function or one-on correspondence f from A to B. If A and B are equivalent, then we denote the symbol A is equivalent to B, and we also explained that equivalent set relation defined on collection of sets is equivalence relation. In this lecture, we will study few examples on equivalent sets. So we'll take first example to be show that open interval 0,1 is equivalent to closed interval 0,1. So here we have to find out some bijective function in open interval 0,1 and closed interval 0,1. In these two sets, closed interval 0,1 contain only two additional points, end points 0 and 1 other than open interval 0,1. For those two points and to define bijective function, we'll take some countable points from both sets separately and remaining common set in both intervals. So for this we'll write 0,1 as open interval 0,1 as half, 1 by 3, 1 by 4, 1 by 5 and so on union A. Close interval 0,1 as 0, 1, then half, 1 by 3 and so on union A, where A is equal to, here A set is equal to open interval 0,1 minus half, 1 by 3, 1 by 4 and so on, which is same as close interval 0,1 minus this set 0, 1, half, 1 by 3 and so on. Now I want to define bijective function between this set and this, and then A to A. Given set is always equivalent to itself under identity map. So for this A to A, I can take every element A is related to itself. But for this, I will map 1/2 to 0, 1 by 3 to 1, 1 by 4 to 1/2 and so on. Okay. So define f from open interval 0,1 to close interval 0,1 as f of half equal to 0 and f of 1 by n is equal to 1 upon n minus 2 for every n greater or equal 3. F of x is equal to x for every x belongs to A. Then from above arrow diagram, f must be bijective function. Then from above diagram, f is 1-1 correspondence, and therefore open interval 0,1 is equivalent to close interval 0,1. Again file proving open interval 0,1 is equivalent to close open interval 0,1 or open close interval 0,1. We'll make such type of adjustment and we can easily show that. Okay. Open interval 0,1 is equivalent to open close interval 0,1. Open interval 0,1 is equivalent to close open interval 0,1 by doing such type of adjustment. We can easily prove that. Then We know that if A is equivalent to B, B is equivalent to C, then A is equivalent to C. So here I proved that open interval 0, 1 is equal to close interval, open, close, open interval. So any two intervals must be equivalent, that we have to show. Boundary intervals by this. So next example, if I take say close interval AB and close interval CD, or open interval AB, open interval CD, open close interval, open close interval, where their ends points are different, then what is the way of defining some bijective function between the two sets? Okay, so define f from close interval AB to CD as, so here I have some close interval AB and here CD close interval. If I relate A to C, this point, and B to D, this is your AC, this is your BD, then if I have a line joining these 2 points, if I find equation of this line segment connecting this point capital A to B, then we are through. So for this x, what is your fx? That you have to find. So fx will become c plus d minus b upon d minus c upon b minus a into x minus a. This is equation of that line. By using 2.4 form of equation of line which I studied in 11th standard, we'll get this equation. Equation of line passing through x1, y1 and x2, y2 is given by y minus y1 is equal to y2 minus y1 upon x2 minus x1 into x minus x1. Y minus y1, y1 I am taking there c. Is it clear? X minus x1, x minus a, and slope of that line d minus c upon b minus a. So in this way, this function must be bijective function. Okay, so fx is equal to c plus d minus c upon b minus a into x minus a. Then f is the equation of line segment joining points A, AC and B, BD in plane. Okay. This fx is bijective function as it is linear function. And therefore, close interval AB is equivalent to close interval CD. On same line, I can prove that open interval AB is equivalent to open interval CD. Open interval AB is equivalent to open interval CD. Close open interval AB is equivalent to close open interval CD. Open close interval AB is equivalent to open close interval DC, CD. And any two intervals are equivalent. So open interval 0, 1 is equivalent to close interval 0, 1. Open interval is equivalent to open interval AB by this. Is it clear? So I can show that any two intervals, bounded intervals, are equivalent. Now what about unbounded intervals and bounded intervals? So try to check whether to open interval 0, 1 is equivalent to whole real line. Open interval 0, 1 is equivalent to whole real line. So if you use, if you remember some functions which we have studied, with help of that, you know that graph of function tan x so tan x graph is like this. Fx equal to tan x from open interval minus pi by 2 to pi by 2 to set of real numbers. F x is equal to tan x f from open interval minus pi by 2 to r. As x approaches towards minus pi by 2, tan x approaches towards minus infinity. And x tends to pi by 2, tan x tends to infinity. And clearly, any horizontal line doesn't curse, or parallel line to x-axis doesn't curse this graph in two or more points, and therefore geometrically this function must be 1, 1 function. And it is bijective also. For every real number on y-axis there is a pre-image in minus pi by 2 to pi by 2, because function is continuous. So fx is equal to tan x is continuous. So I can prove that any two open intervals are equivalent. Therefore open interval 0, 1 is equivalent to open interval minus pi by 2 to pi by 2. And by this function, this is equivalent to r. Therefore, by some function f, it is related to this. By this, it is related to this. So G composite f from open interval 0, 1 to r is bijective function. So here I will find line segment equation. And here G is nothing but tan x. Then G composite f will become bijective function. And in this way, open interval 0, 1 is equivalent to r. Try to prove that open interval 0, 1 is equivalent to open interval 0, infinity. For that, you have studied beta function, gamma functions, etc. In that you have studied what is the bijective function between that two. Okay, try to find that. So with these few examples, we'll start our next concept: countable set, uncountable set, etc. So what is a finite set? Finite set is a set which contains precisely n element for some positive integer n, or n belongs to set of natural numbers. If I have set A is equal to say a1, a2, dot up to an, then this set must be equivalent to 1, 2 up to n is equal to n to the suffix n. So if some given set is equivalent to set containing first n natural numbers, then we say that A is finite set containing n elements. Empty set is finite because number of elements in that set is equal to 0. And if given set is not equivalent to any finite set containing n natural numbers, then that set is called as infinite set. That set is called as infinite set. Now in infinite set also, what will be the sizes of that infinite set? The smallest infinite set is countable set or denumerable set. Countable set or denumerable set. From school level, we are calling set of natural number as set of counting numbers. 1, 2, 3, 4 and so on. Means one after one we are counting numbers. Means set of natural number itself is countable set. So if you are able to count elements in given set by arranging them sequentially, in given set first element, second, third, so on. Okay, means we are assigning natural numbers to elements in that set. 1 to first element of set, 2 to second element of that set, 3 to third element and so on. If we are able to find bijective function from set of natural number to that particular set A, then n is equivalent to A. A set which is equivalent to set of natural number is called as countable set or denumerable set, according to R.R. Goldberg book, because in some books countable set is taken to be set which is finite or equivalent to set of natural number. So other books, other authors are treating finite set as one countable set. But according to Goldberg, denumerable and countable set concept is one and same. In that, denumerable set is nothing but our countable set here. And that's why concepts depends on book, which book we are following. Depending on that also, while proving the results, we have to use these concepts used in that book. If I have to show that some set is countable according to some other book in which countable set is taken to be finite or set which is equivalent to set of natural number, then firstly you have to check whether it is finite. If not, then you have to show that it is equivalent to set of natural number. But here if I have to check some set is countable, then I have to just show that it is equivalent to set of natural number. Okay. So what is a countable set? A set A is countable if A is equivalent to set of natural number, that is, if there exists bijective function f from set of natural number to A. So f relate if f of n is equal to an or every n, then A is written as A1, A2, A3 and so on. First element of A is A1, second is A2 and so on. So this set, countable set is also written in this way. Countable set is also written in this way. Suffixes are elements from set of natural number. Domain for that function. So natural number set is itself countable. Now, what are other countable sets? If I take Z, this is 1, 2, 3 and so on. Here 0, 1, minus 1, 2, minus 2, 3, minus 3 and so on. 6, 7, 8, 9 and so on. And relate 1 to 0, 2 to 1, 3 to minus 1, 4 to 2, 5 to minus 2, 6 to 3, 7 to minus 3 and so on. Means I am assigning odd natural number to 0 and negative integers, while even natural number to positive integers. Okay, so from this, f from n to z defined as f of n to n minus 1 is equal to minus of n minus 1, minus of n minus 1. Okay, if I put n equal to 1 here, 1 minus 1 gives a 0. If I put n equal to 2, then okay, f of 2n is equal to n. f of 2n is equal to n. Now f of 1, if I put 2 now here, is it clear? F of 2n is n, f of 2 is 1, f of 4 is 2, and so on. F of 2n minus 1, if I put n equal to 1, then I am getting 1. If I put n equal to 2, 4 minus 1 is 3. Okay, and in 2 minus 1, that is 1 minus 1. If I put n equal to 3, 6 minus 1, 5, that is minus 2. 3 minus 1, 2 minus 2. Okay, or that is, if I write fn is equal to n minus 1 if n is odd. N is odd, sorry, by 2. And fn is equal to n by 2 if n is even. Other way, or this way. Then this function is bijective function. Therefore, set of natural number is equivalent to z, and therefore z is countable set. Z is countable set. Here, natural number 0 negative integers, which is a superset of natural number, it is equivalent to set of natural number. I am taking union of countable sets. Means firstly, natural number is equivalent to natural number, so among these 1, 2, 3, dot dot etc. That set is equivalent to set of natural number. If I take just set of negative integers, it is equivalent to set of natural number, and inserting 0 there, some finite set. It is also equivalent to, means I am inserting their set of integers in some sequence so that we can easily define some function. This is useful to construct that if A and B are two countable sets, A is equal to A1, A2 and so on is countable, B equal to B1, B2, B3 countable, then A union B is equal to A1, B1, A2, B2 and so on. Means I will map one natural number to A1, second to B1, third to A2, fourth to B2. So in this way, by writing elements in A union B alternatively, I can count elements. I can assign natural number to them, but by the writing union some elements may be repeated, we'll ignore that elements from that. So this set becomes countable set. So union of two countable sets is again countable. Our aim is to prove that countable union of countable sets is countable. And then for set of rational numbers, you know that set of rational number is a set containing numbers of type p by q where q is not equal to 0. So if I take EQ set to be p by q where p here is in set of integers, then that EQ set is equivalent to set of integer where q is fixed, means, and z is equivalent to set of natural numbers. So easily I can show that EQ is equivalent to set of natural number. So every set of rational number in which denominator is q is countable. And then countable union of countable sets is countable. With help of that, I can easily prove that set of rational numbers is countable set. So with this discussion, we'll stop our today's lecture. Thank you. We'll meet by tomorrow.